touchdown. So the one nice thing about Ha ya bu sa 2's system, sampling system, is you have a chance to collect several different types of material from Ruby. So that's very good. Question right here.
Hazards. Who, what, and how would you be passing on your findings? And how do you hope this information would help us in the future?
So at NASA, well, we have a special office at NASA. It's called the Planetary Defense Coordination Office. We at NASA work with colleagues at JAXA, colleagues at ESA, colleagues in Russia, because planetary defense is a worldwide issue. So we have set up with the United Nations a couple of organizations. One is the International Asteroid Warning Network, International Asteroid Warning Network. So it's a cooperative agreement to help look for dangerous asteroids before they hit. The other group is called SAME page, which stands for Space Mission Planning Advisory Group. And that's in case we see something dangerous, hopefully with many years warning. And they came up with ways of sending spacecraft to analyze, study, and deflect the asteroid. One of the other things that I am working on, I don't just work on Ha ya bu sa 2 and OSIRIS-REx. I would love to work on just those missions, but I have to work on other missions as well. And the United States, NASA, is working on a mission called DART. DART, just like a dart, is a planetary defense demonstration. We are planning to launch a spacecraft in 2021 that will practice deflecting, pushing away an asteroid, a near-Earth asteroid. So we're hoping to use this mission to learn about planetary defense and how we could push an asteroid away. The asteroid target we have is a little bit smaller than Ryugu or Bennu. It's about 150 meters in size. So all of this information we gained from our ground-based telescopes, this test mission, it will all be put forward to NASA, to ESA, to the world in order to help coordinate, just in case you see something coming. Think of us as insurance. Hopefully you never need us, but you'll be very happy that we're here.
I'm Suzuki Saori, it's me, Vega. And I have a question, but my pronunciation is not good, so I want to speak Japanese.
大丈夫です。
すみません。数年前に JAXA の方とお話をしたときに、地球に隕石がぶつかったときに、ぶつかる前に ミサイルを一発発射するっていう話をしてたんですけど、ベロベロに酔ってたのでどこまで本当か分かんないんですけど、一発目は確かに当たるけれども、2発3発目を当てるのがとても難しいという話をされてたんですね。でその計算方法っていうのが3年まではまだわからないっていうお話をされてたんですけれども、その後はどのようになったのかなと思ってできれば教えていただきたいなと思いまして質問しました。お願いします。
It's a nice question. So with missiles, total kind of thing, not good. So by the time the asteroid is in range of missiles, it's too late. So that's not to say that if all else failed, right, we've tried many other things. Maybe, of course, we would try missiles. Maybe. But it's very unlikely that it would work. The best thing we do is we need to find the asteroids first. So we have lots of time. And then we can send spacecraft, like the DART mission, similar, that takes several years to get to the target, to hit, and then move it away. One of my famous advisors, three things that were very important for asteroids. You're going to defend the planet. One is find them early. 2 is find them early. 3 is find them early. You have to know they're coming because it takes so long to send a spacecraft to deflect an asteroid. One of the things is, unlike the movie Armageddon, Totemo Kanoshi desu, really bad. But we don't blow up asteroid, right? Because what happens is you make an asteroid single, now multiple, and if you are not successful, taksan asteroid, worui, totemo worui, really bad. So we'd like to deflect, push away the asteroids. And so our best method, we think, is to ram into the asteroid at very high speed. For example, the DART spacecraft will hit the asteroid at 6 kilometers per second. Very, very high energy to push the asteroid away. It's a test. And this is what we would do if we saw an asteroid coming, we think, first time. Hopefully that explains a little bit. Missiles, no good. Thank you.
We have time for just one more question until this gentleman with his hand up first.
Thank you for a wonderful presentation. So you said in the final presentation slide, so one of the objects in your activity is the science. So I'm working in the German chemical company, so I have interest in the origin of the organic materials. So I have one simple question. What percentage can you find out organic material? For example, amino acid, fatty acid, or the sugar in the space outside of Earth?
So it's a very good question about how much organic material is in the meteorites. It really depends on the meteorite. It depends on the history of the meteorite, of the asteroid, I should say. So we have meteorites on Earth, and some of these have lots of organic material. Amino acids, for example, and many different kinds, but different levels of abundance depending on the thermal history, and the aqueous alteration. So in other words, how hot the parent asteroid got, or how wet that asteroid also got. Hopefully, the idea with Ryugu and Bennu is when we get those samples, we will be able to tell exactly. That's the nice thing about sample return, is we have what we call ground truth. The issue we have right now is we have carbonaceous meteorites. These meteorites we think come from asteroids like Ryugu and Bennu. They're on Earth, but we don't know exactly where they came from in the sky, which asteroid. It's like going to a stream in Japan, a mountain stream, and you find several rocks in the stream. You know they came from the mountains, but you don't know exactly where or which mountain, right? But you know they came from there. What we're trying to do